Let's talk about limits like this. Let's suppose we've got the limit as x goes to infinity, or it could be negative infinity, but let's suppose that x is either going to positive or negative infinity, and let's suppose it equals some limit. What does that mean? That's what we're going to explore now. So let's suppose that this little horizontal broken line here is L. And what we're saying is this function, as x goes to infinity, as x goes, out in the positive direction, gets larger and larger and larger, the function f of x goes to this number L. Well, what does that mean? So what I've drawn here is I've drawn in red the function f of x. And what it might look like that would fit this, limit. So one of the things that you might connect to here is this notion of horizontal asymptotes, which you've seen before in pre-calculus or college algebra. So what we're really going to look at here are, you can think of as horizontal asymptotes. We're going to be a little more rigorous in how we view them. So, but still, as a connection, think of the horizontal asymptotes. So here is this function, and here is the limit. Now, notice that every part of this function here, the high point and the low point, it's all contained. It has an upper bound here and a lower bound here, right? In other words, if I said I'm going to graph this this line here, this horizontal line, up here, whatever this is L plus some epsilon. I'll call it epsilon 1. And this down here is L minus epsilon 1. Where this distance, whoops, you can't see it, there we go. Where this distance here is epsilon 1. So, and I make a horizontal line here, this entire function is contained within that. In other words, it doesn't have any values bigger than L plus epsilon 1 or any values smaller than L minus epsilon 1. Well, that's for epsilon 1, but what if I make choose a different epsilon? What if I choose this right here and this right here? In other words, I make it epsilon 2, L plus epsilon 2, where my epsilon is a little smaller. Epsilon is that, okay? Well, you notice that not the entire function is within that, is within those bounds. However, if I go over far enough, like, okay, so here we have outside L plus epsilon 2, and here and here we have below L minus epsilon 2. However, if we come over here, look at this right here. If I come to this value for x, from that point on, every part of this graph is within this little epsilon 2 neighborhood, where this is epsilon 2, and this is epsilon 2. So every part of this graph is contained within L plus epsilon 2 or L minus epsilon 2. And you might say, okay, well, what if I make the epsilon smaller? Okay, what if I go this route? I go down another one, and I have L plus epsilon 3, where epsilon 3 is a little smaller. And I draw a horizontal line there. Well, obviously the graph is not contained in that. Right? Not all of it. However, if I go over far enough to right here, look at this. This value for x on, the entire function is contained in there. So, and here's the deal. No matter which epsilon I choose, let me choose an epsilon very small. Okay? This little epsilon here. And I make a horizontal line over. Well, it takes me a little while to go out far enough, but I get to the point where the entire graph is contained between these two lines. See, look at that right there. From then on, the entire graph is contained. Well, what this means, this limit right here, what it means is for every epsilon I choose, no matter how wee the epsilon is, no matter how small it is, if I go out far enough, I can find an x value so that from that point on, the entire function is contained within those two horizontal lines. That's what this limit means right there. So that when we say that, But now you can think of it as, a horizontal asymptote because, that's what it is. This is a horizontal asymptote. And notice with a horizontal asymptote, it's okay if the function crosses the horizontal asymptote. There's no worries there because some people think, well, asymptotes can't be crossed. Well, horizontal ones can. Yeah. Okay, so let's look at some basic ones. Let's suppose that we've got the limit as x goes to infinity of 1 over x. And we want to figure out, well, what is that limit right there? In other words, what we're trying to do is figure out what the horizontal asymptote is. But let's just think about this a minute. Let's see what happens with a function like this. And we can do so by just looking numerically at some values for x and then some function values. So let's suppose that we've got 1 over x, that's our function. And we do this. We say, okay, I'm going to plug in a 1. I'm going to plug in a 10. I'm going to plug in 100, 1,000. I'm going to plug in these values, maybe even a 10,000. Okay. And let's see what the corresponding function values are here. Okay. So if we plug these in, notice, first of all, when we plug in a 1, we just get a 1. When I plug in a 10, I get a 0.1. When I plug in 100, I 0.01, 1,000, 0.001, 10,000, 3 zeros and a 1. And you can see what happens here through these powers of 10. What happens is, as x goes out to infinity, this thing tends towards 0. And so we would say this. We would say this limit is 0 because that's where the 1 over x is ending up. Now, if it wouldn't matter if we went in the negative direction, right? We could say, well, what happens as x goes to negative infinity? Well, if x goes to negative infinity, we're just going to still have 0, okay? The function is, in other words, is still going to tend towards 0. Now, that's going to be the case for situations like this, where you have the limit as x goes to infinity, and you have 1 over, let's say x to the alpha, where alpha is greater than 0. When you have a situation like that, this function, this limit is definitely going to be 0. So this is going to be 0. That's going to be that limit. And that's going to happen whenever you have a bigger power on the bottom. Now, it doesn't just have to look like this, x to the alpha. You could have something like this. You could have limit as x goes to 0 of 1 over e to the x. Well, this is certainly going to grow fast. In other words, look at what's happening here. You have the top. That's just a constant. It's not changing at all. But the bottom is blowing up like crazy. So that limit's just going to be 0. Now you have to be careful. Let's suppose that you have a situation like this. Let's suppose you have the limit as x goes to infinity, and you have 1 over e to the negative x, something like that. Well, that's going to be a different situation. Look what that is. Let's just rewrite it. In other words, yeah, you've got this exponential thing in the bottom, but look what happens. As you go to infinity, you've got e to the x. Well, that certainly doesn't go to 0. That just explodes. That gets large. Let's just denote that as that goes to infinity. It gets larger and larger and larger and just completely blows up. So you have to be careful. You have to make sure that you're looking at it correctly, because if you look at 1 over x to the negative x, it's a different situation. Now, let's suppose that we've got the limit as x goes to negative infinity of e to the x. Now, notice what that is. X is going to negative infinity. That means you're putting in negative values for x. That means that's the same, if you think about it, as the limit as x goes to infinity of 1 over e to the x. Okay? So there's some trickiness to this. So you have to be careful. Now, what I want to do, since a lot of this just involves thinking about horizontal asymptotes, when you're trying to interpret the limit, when you're trying to evaluate the limit, a lot of it just involves horizontal asymptotes. So I've got a little video I want to insert here that I made for college algebra, just to remind you about horizontal asymptotes and the cases that we use to find horizontal asymptotes. Now, how do we find the horizontal asymptotes? That's the question. Well, we're going to look at three cases. Case one is a situation like this. And now what I'm doing is I'm just writing a very simple one. Ax to the n plus b, and this could be a lot more complicated. This could be ax to the n plus bx to the n minus 1 plus c x to the n minus 2, and so forth. I'm just writing a very simple polynomial here up top, a very simple one on the bottom, and I'm just using n. Now you see here that the degree of the top and the degree on the bottom are the same. So this is case one, when the degree of the top and the degree on the bottom are the same. How do you find the horizontal asymptote in that situation? Well, let's take a minute and just explore this. Let me multiply the top and the bottom by 1 over x to the n. Just a little trick to help us to see what's happening as this x goes to infinity. And I took the largest power here and I just divide it by x to the n on the top and the bottom. Now it's fine to do that because this is like multiplying by 1, right? 1 over x to the n divided by 1 over x to the n. Just like I'm multiplying by 1. Now if I distribute through there, and multiply each term on top by 1 over x to the n, this is what I get. Now notice this cancels, x to the n over x to the n, x to the n over x to the n here. Okay, so those are taken out, and here's what we have left. Now, look, as x goes to infinity, look what you have here. You have a constant over this thing that's growing larger and larger and larger right here. Well, when you have a constant over something that's getting increasingly large, that's just going to be 0. Now we have 0 here and here. So here's what we find. As x goes to infinity, this term and this term go to 0. And all we're left with is a over c. The ratio of the leading coefficient. So here's case one. If you have the degree of the top and the degree of the bottom are the same, the horizontal asymptote is the ratio of the leading coefficients. In this case, it's a over c. Now let's look at case two. Let's suppose the degree on the bottom is bigger. Now we're assuming here that k is some positive number. Okay. And so we have ax to the n up top and cx to the n plus k on the bottom. So the bottom has a bigger degree. And of course, we're saying k is some positive integer, okay, or some positive natural number, let's say. That's a better way to say it. But the degree on the bottom is bigger than the degree of the top. Okay, so let's see what the horizontal asymptote might be. In other words, how does this function behave as x goes to infinity? Well, I'm going to multiply the top and the bottom by 1 over x to the n plus k. So that's the trick I'm going to use here. If I distribute 1 over x to the n plus k, I get this situation. Now notice some things will cancel, and I'm left with this. Now, dig this. As x goes to infinity, this first term goes to 0, the second term goes to 0, and then the last term down here goes to 0. And all you're left with is 0 over c. Well, that's 0. So as x goes to infinity, f of x goes to 0. So we say here, in this case, where the degree on the bottom is bigger than the degree of top, the x-axis is the horizontal asymptote. Or, y equals 0. Now, case 3. So let's look at this case 3, and It's the case where the degree on the top is bigger than that of the bottom. So if you look at this, and let's do this trick. Let's multiply the top and the bottom by 1 over x to the n to kind of illustrate what happens as x goes to infinity. And if we do that, here's what we get. X to the n under the first term, the second term, same thing we've been doing. But notice what happens. These x to the n's cancel down here. And over here, you've got this term, and this right here. Now, notice that these two terms go to 0. And what we're left with is ax to the k up top and just a constant on the bottom. Well, if you've got this x growing up top and just a constant on the bottom, what you have is a situation that as x goes to infinity, f of x goes to either positive or negative infinity, depending on what the signs are. So there is no horizontal asymptote in this case. Okay, so some examples here very quickly. Let's suppose that we've got the limit as x goes to infinity of 5x to the fourth plus 7x squared plus 5. And down here we've got 6x to the fourth plus 9x squared plus 10, something like that. Now, this is just a rational function, one polynomial over another. So this is going to be the case where the degree on the top and the degree on the bottom are the same. So this one is going to be the ratio of the leading coefficients, 5 over 6. Now let me modify this a bit because we want to remember we have to be careful. So let's suppose I've got this same thing, 5x to the fourth plus 7x squared plus 5. And down here basically the same thing. I've got 6x to the fourth plus 9x squared plus, let's say, 2 to the x. 2 to the x. These exponential functions grow very fast. And if you have an exponential function down like this, it's different than just having one polynomial over another. These exponential functions tend to dominate. And the fact that this exponential function is in the denominator and your x is going to positive infinity, that tells me that this bottom here is getting small, it's getting large very fast. So this is just going to be 0. That limit is going to be 0. So you have to be careful. Now, if I modify it a little bit, if I say, well, what about if x goes to negative infinity? And I've got this same thing, 5x to the fourth plus 7x squared plus 5. And notice this is going to negative infinity now. This is 6x to the fourth plus 9x squared plus 2 to the x. Let me still do that, 2 to the x. Okay. Now, if I've got this situation, let me give you a better 2 to the x there. Let me see if I can erase it better. Okay, make it more clear. Okay, so we've got this 2 to the x. Now, this time, x is going to negative infinity. So this term right here is being raised to a negative power. Well, if you think about it, if you see what's going on there, if you have 2 to the negative power, think about that. We have x, and let's just look and see what happens here. We've got 2 to the x. And let's just start putting in some powers. Let's put in -1, -2, -3, -4. What happens here? 2 to the -1, that's 1/2. 2 to the -2, that's 1/4. 2 to the -3, that's 1/8, 1/16. So you can see here what's happening. As x gets larger and larger in the negative direction, this term right here goes to 0. So this limit would just be 5/6. So you just have to be careful with situations like that. Now, let's look at another one. Let's suppose we've got the limit as x goes to infinity of, let's say, 5x plus 1 over, oh, let's say here the square root of x squared plus 2. Now, this time we have a little bit of a problem here because it's not just one polynomial over another, it's a polynomial over this square root thing down here. So that can, that can give us some grief. But here's what we can do. Let's, in an attempt to simplify this and help us to understand what's going on, we can do this. Let me just go inside this radical and think about, I'm just going to divide, here's what I'm going to do. I'm going to divide the top and the bottom by x. I'm going to multiply by 1 over x on the top and the bottom. And this will help me to see what's going on here. Okay, so up top, let's see what we have here. We've got the limit as x goes to infinity. And we've got 5x over x. Well, 5x over x, that's just 5, plus 1 over x. See? I just multiplied by 1 over x to each one of these, and I got 5x times 1 over x. The x's cancel. So I just got 5 plus 1 over x. Now, down here, I've got this radical times 1 over x. Well, I'm going to bring that 1 over x inside the radical, and when I do that, it's going to be, I bump it up a power, right? When I bring it in underneath, it's going to be x squared underneath if it's x on the outside. Okay, so here's what we've got. Down on the bottom, and notice x is going to positive infinity. So x is positive. We don't have to worry about, anything that comes into play when we're dealing with negative x's. So I bring in a negative x, and I've got x squared over x squared. See, I brought that x underneath, so it's x squared, plus 2 over x squared. Okay? Now, let's see what we've got now. If you look at this, let's see here. We've got the limit as x goes to infinity. Okay? Up top, we've got 5 plus 1 over x. And on the bottom, we've got the square root of 1 plus 2 over x squared. See that? Now what happens to this thing, 2 over x squared as x goes to infinity? Well, it goes away. It goes to 0 is what happens. You've got 2 over x squared as x goes to infinity. This 2 over x squared just goes to 0. And also, this goes to 0. 1 over x goes to 0. So all you're left with is 5. So this limit is 5. So that's the way so really you didn't have to go through all this process here. You could just say, you could kind of just ignore this square root in this case. You could say, well, really, as x gets larger and larger and larger, what you really have here is 5x over x, which the ratio of the leading coefficients is 5. So you could kind of just, since x is going to infinity, positive infinity, you could say, well, this is just getting it's getting closer and closer to the square root of x squared because the 2 is mattering less and less. So the square root of x squared is x. Since x is guaranteed positive, x is going to infinity. You have 5x over x. Ratio of leading coefficients is just 5. That's the way you could do it.